Okay, so let's see. We want this bigger. Can I just drag it? Yeah. Okay. Has Mr. Webster arrived? No. Okay. All right. Let me just briefly mention something about Laplace transforms. You know, when we talked about convolutions and Fourier transforms, we had the very nice relation that the Fourier transform of a convolution was the product of the Fourier transforms. A similar result holds for Laplace transforms, but only if one redefines what one means by a convolution. And this other definition was invented by Vito Volterra. And let me see if I can, yes, all right. I added a section of this. I think what I'll do is I'll make a PDF of this, and I guess I'll just put it on the class website, and you can take it if you want it. So it's a very simple idea. So let me turn the lights out for this, because I don't want to dwell on this business. So Volterra defined the convolution differently. The ordinary convolution would have an integral over y here going from minus infinity to plus infinity. Volterra's definition goes from 0 to x. And so then, if you take the Laplace transform of the Volterra convolution, you wind up with the product of the Laplace transforms. And so I just mentioned that to you. I don't think this is something that you need to. I think it's something you need to be aware of, but. By the way, in this derivation here, one is interchanging the order of integration in a way that's worth thinking about. Here one is integrating x from 0 to infinity, and y you go up to x. Whereas here we're going y 0 to infinity and x from y to infinity. And if you draw a picture of the two regions of integration, you'll see that they're actually the same. Maybe I should do that for you on the board. So let me draw this. So the first case, x goes from 0 to infinity, and y just goes up to x. So we're talking about this region here. If we do it this way, we're integrating on y from 0 to infinity, but we're only integrating on x from y to infinity. So what we're doing is we're going this way. And you see it's the same region of integration. So this is a change of variables that in integration that's a little bit different from the ordinary change of variables in integrations. As usual, you should ask questions, and if you have them, and so let me skip ahead to to infinite series, and in particular to the factorials. And in fact, because the factorials and the gamma function are really important, I think I'm going to do these on the board. And I don't know if that helps any, but I think it might. So you know, of course, what n factorial is. It's n minus 1, dot, 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 down 2 and 1. And as I said before, 0 factorial is 1. And Stirling, a long time ago, derived the approximation of square root of 2 pi n over e to the n. And then subsequent people have derived other corrections to this, and in particular, Merman's is the best. Merman's second correction is 1 over 12n minus 1 over 360 n cubed plus 1 over 1260 n to the fifth. So this is Merman's second correction, which is remarkably accurate. In one of the applications of factorials is the binomial coefficient, which is defined as a ratio of 3 different factorials. And let me quickly go on to just remind you again of Leibniz's formula. And this is the sum k equals 0 to infinity. And the binomial coefficient appears. And this is then the kth derivative of f of x and the n minus kth derivative of g of x. This is a nice notation, kth derivative, n minus kth derivative. There are many, many notations for derivatives. Double factorials, 2n minus 1, double factorial is 2n minus 1. You basically skip things, so it's 2n minus 3, dot, 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 down to 1. If it's an even thing, 2n double factorial is 2n minus 2, down to you end at 2. And it turns out that 0 double factorial is the same thing as minus 1 double factorial, and both of them are equal to 1. Okay, so these are a variety of definitions that you should make your own. The formula for the generalization of z factorial is to write it as an integral e to the minus t to the z dt. Now, if you set z equal to an integer and ask Mathematica or Maxima, actually, you know, I was trying Maxima in my office, and it's not the world's greatest on doing integrals. Mathematica does a great job. Okay, anyway, if you set z equal to an integer, then this gives you n factorial for an integer. On the other hand, the integral generalizes the integer value, the factorial function, from integer values to complex values. And so that is the generalization. Unfortunately, well, all right, let me just show you. Obviously, then, if we do 0 factorial, well, we just set z equal to 0, so we have integral 0 to to infinity, e to the minus t, t to the 0, that's just 1. Remember, anything to the 0, or almost anything to the 0 is 1. And this is a simple integral, and that is 1. So that's why 0 factorial is 1. Unfortunately, the mathematicians, instead of defining this as the gamma function, perversely defined the gamma function with an offset of 1. And so this is equal to the integral 0 to infinity e to the minus t, t to the z minus 1 dt, which of course is z minus 1 factorial. Factorial. I'm having trouble pronouncing factorial. Anyway, that's the gamma function, and I don't know why they did that. It strikes me as this has caused innumerable errors and all sorts of problems for students and probably for mathematicians and physicists as well. In any event, the actual formula then is z factorial is gamma of z plus 1. Nonetheless, the gamma function, so defined as this integral with complex z, what we'll see is that it's well defined throughout the complex z plane, and it just has problems when z is a negative integer. And we'll see that, in fact, in a moment, because we can write gamma of z plus 1, which of course what they should have defined as gamma of z, as an integral 0 to infinity minus d by dt of e to the minus t. Of course, this is just equal to e to the minus t. T to the z, you do dt, you do the integration by parts, and you get 0 to infinity e to the minus t. The t derivative of this, which is z, t to the z minus 1 dt. And now you see this is just z gamma of z minus gamma of z. So this is z gamma of z. So this is a really important relation. Gamma of z plus 1 is z gamma of z. That's something that you should think about a lot and make sure you understand where it comes from, this integration by parts. And the reason why this is smooth is that the boundary terms vanish at 0 and infinity. At 0 they vanish because of the t, at infinity they vanish because of e to the minus t. Now, we'll see when we study complex variable theory that this is really quite significant. But just for a moment, we can just see that gamma of z plus n, well, this is z plus n minus 1, gamma of z plus n minus 1. In other words, this is, you just replace z by I guess, z plus n minus 1, and you get this and that. And then you iterate that, and what you get is that this is z plus n, minus 1, z plus n minus 2, dot, 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 eventually down to z gamma of z. And now, if you take a ratio of gamma of z plus n divided by gamma of z plus m, what happens is the complicated part, namely gamma of z, cancels, and what you're left is a bunch of factors like this in the numerator and in the denominator, and when you cancel them all, what you find is that this is z plus n minus 1 factorial divided by z plus m minus 1 factorial. So in other words, the gamma function is apart from the stupid offset, the gamma function is the factorial function. And so you expect a ratio of these two is a ratio of factorials. And it works out and really is. Something that's more important is you can invert this thing. And what you can do is you can write gamma of z. In other words, you just invert this line, this relation to start with. You write that as 1 over z times gamma of z plus 1. And then you repeat that, and you get that this is equal to 1 over z plus 1, gamma then of z plus 2. And so eventually what you have is 1 over z plus 1, 1 over z plus 2, so forth. And well, at this point you have gamma of z plus 3. So in other words, you can express gamma of z in terms of things that are farther out to the right in the complex z-plane, modulo these terms. And notice that these terms are are singular at the negative integers. So that's what I said to you before, that the gamma function is so analytic everywhere except at these negative integers. For that matter, 0. Okay, I think that's enough of that's the stuff that's really important. Let me now go more quickly over the stuff that you should know about, but that is less important. You see, I've already skipped some of the stuff that I think of as. So, Euler and Weierstrass were some of the great mathematicians of the past, and Euler was able to express the gamma function in as an infinite product, and Weierstrass did the same thing, but a different infinite product. You can also show that the gamma function takes this form, and you can derive these relations. Now, one of the useful thing, the reason why people like the gamma function, in fact, in some sense, the gamma function is one of the most important functions of mathematics. I mean, we have exponentials, and in terms of exponentials, we have sines, cosines, coshs, and sinus, and so forth. Beyond that, the next most important thing is probably the gamma function, because it generalizes the factorial function. It generalizes n factorial from integers to z factorial. And so anytime you have something like, for example, the Bessel function is a sum like this, where this is actually m plus nu factorial, where nu is an integer, but now we can just have generalized and define the Bessel function for not just as an integer j sub n of rho, but j sub nu of rho, where nu is a complex number. And so we have an immediate generalization of anytime we have a series, or often when we have a series representation of a mathematical function, it involves factorials, and you can then generalize it to complex values of the factorial, and so you've generalized your Bessel function enormously here. Here's the spherical Bessel function being generalized. One thing that's important in numerical analysis, which you'll find if you use a computer to do things with factorials, what you might find is that the computer's very happy computing 6 factorial or 10 factorial, but if you push n past 100, you find that the computer can no longer handle a number that big. And what you need to do is instead work in terms of the logarithm of the gamma function, or the logarithm of n factorial. And there's a Fortran function, it's called log gamma of x, a C function, L gamma of x, MATLAB function, gamma ln, a Python function, log gamma, and they all give you log of gamma, which is log of x minus 1 factorial for real x. So that's just something to keep in mind. If you're, as physicists, we've got to deal with huge factorials. For example, Avogadro's number might show up, it shows up in physics problems, and if you try to have a computer compute Avogadro's number factorial, you'll just, it'll just give you an error message. So instead you go for logarithms. Euler defined a beta function, and you can figure out what the beta function is. It turns out it's defined this way, but one way of understanding it is to take the numerator and change variables, and then what you find is that the product of gamma of x times gamma of y is actually gamma of x plus y multiplied by a fairly simple integral, which is the beta function. So beta function of x and y is twice an integral 0 to 2 pi of this expression here, and you can, if you change variables again, you get this expression. And you can, an obvious generalization of the beta function is you just go to n gammas in the top and the sum of all the arguments in the bottom. All right, any questions? Taylor series. I'm sure you've learned this several times as an undergraduate, that f of x plus a is f of x plus a times f prime, a squared over 2f double prime, and so forth. And then there's an error term. Turns out the error term for a function that has continuous nth derivatives, or continuous capital nth derivative, the error turns out to be a to the n over n factorial times the value of the nth derivative evaluated at some point between x and x plus a. That's kind of interesting. Anyway, another way of writing this thing is to say if f of x plus a is an infinite series, a to the n over n factorial times the nth derivative of f at x. And another way of writing that is to take f of x and operate on it with e to the a d by dx. So if you expand that, it gives you this. And in quantum mechanics, the momentum operator acting on the right is h bar over I d by dx of the bra x. And so the wave function at x plus a is the inner product of the ket. No, it's the bra at x plus a with the ket psi. But x plus a is x e to the I a p over h bar. And that's because P is h bar over I d by dx. So that just reproduces this expression here, and in other words, it reproduces it this way. So psi of x plus a is e to the a d by dx acting on the wave function at x. And that's why the momentum operator does this. By the way, one of the essential things that distinguishes quantum mechanics from classical mechanics is that the momentum operator generates space translations. The energy operator, or the Hamiltonian, generates time translations. You can think of a Fourier series as a power series, and what you do is you just recall what the coefficients are, and or equivalently, you take this sum and you split it into two sums. Both of them, you change the index so that both of them go forward in n, from 1 to infinity and 0 to infinity. And the variable, this exponential, you can write in terms of z, setting z equal to e to the I 2 pi x over L, and z inverse to be the same thing with a negative exponent. You then see that the radii of convergence of these two power series by the, I guess it's called the ratio test, is given by R plus inverse is this, R minus inverse is that, and so the power series, which is really the Fourier series, converges as long as absolute value of z is less than R plus, and 1 over the absolute value of z is less than R minus. On the other hand, the absolute value of z is unity, and so what you must have is that R plus has to be bigger than 1 over R minus, and within that range then, and 1 has to lie within that range. If so, then you have absolute and uniform convergence of the Fourier series. I give a simple example here, but it's not worth dwelling upon. The binomial series is, for example, well, you must have learned this repeatedly as undergraduates. 1 plus z to the a is a, let me make this a little bit bigger. Let's see what happens if I make it. Yeah, well, maybe not that big. Maybe that big. So 1 plus x to the a is this sum, and it's, well, successive powers look like this, and you can rewrite it this way. And if a is actually an integer, then it's a very nice expression, and it terminates. But if a is not an integer, it's an infinite series. And once you've derived that infinite series, the one for x plus y to the a is this. And again, if a is an integer, the thing terminates and you get this expression. These are called the binomial theorem. Do you guys want to see something about neutrino oscillations, or should we skip that and do it Wednesday, or what? All right, I'll skip it since nobody wants to hear about neutrino oscillations. Binomial expansion is also, you can use it to solve some expressions exactly. As I said, when a is not a positive integer, the series doesn't terminate, and two important examples are the square root of 1 plus x and 1 over the square root of 1 plus x. They turn out to be fairly simple series. Another is the log of 1 plus x, and these are all Taylor series, and if you compute the derivatives, you find that log of 1 plus x is this series, and it converges in this region here, and slowly. If you replace x by minus x, you see you get this expression, and so the log of the ratio is that. So now, you should have sort of a nodding familiarity with what a Dirichlet series is. A Dirichlet series is something that in which the nth term is 1 over n to the z. And so they're of this form, c sub n over n to the z. One example is the Riemann zeta function, which is an important function of mathematical physics. That's the simplest case where all the cn's are equal to 1. So it's a sum from 1 to infinity, 1 over n to the z power. This series has some convergence for the real part of z positive, greater than 1, and there are some amusing values of the sum. Zeta of 2 is pi squared over 6. Zeta of 3, well, it's just 1.2 roughly. Zeta of 4, though, is exactly pi to the 4th over 90. And zeta over 6 is pi to the 6th over 945. So some of them have simple forms, others, I don't know any simple expression for zeta of 5, but there may be. Mathematica has a service, I forget what, I think they call it Wolfram Alpha. You can give it an approximation like this and ask, what is that? And, well, it'll probably reply that it's zeta of 3, but it might give you something else that's more interesting. I don't know, I haven't tried it. Anyway, Euler showed, and this is one of the remarkable results of classical mathematics, that for real z greater than 1, the Riemann zeta function can be represented as an infinite product over prime numbers, all prime numbers. And the product is 1 over 1 minus p to the minus z. So that's you know, just remarkable. The zeta function shows up a lot in Planck's distribution of, and this Planck's distribution, of course, is extremely important. It's what you'd use as a basis for a scientific discussion of global warming. It's what started quantum mechanics, because Planck introduced his constant h in this expression. And what he showed was that the electromagnetic energy in a closed cavity of volume V at temperature T between for frequencies around nu of width d nu is given by this expression. And from that you can derive all sorts of things. But when you do the integrals to derive these things, you find that a zeta function pops up. And if you want, we can go through this slowly in the problem session tomorrow, room 5. And we do it now at 10 of 5. Is that right? That's when we start? Is that right?
Yes.
Okay, thank you. You can skip the Lerche transcendent. I don't know why the hell I put it. Bernoulli numbers, again, I don't think that you have to knock yourself out over Bernoulli numbers, but you should have seen them once or twice, so that if you see them later, you don't say to yourself, what the hell is that? Instead, you say to yourself, oh, I remember, I once knew what they were, and I can find out. So we go to chapter 5 and I'll find out what they were. Anyway, they're defined in terms of the generating function, x over e to the x minus 1, as the coefficients of the power series of the generating function, and the nth derivative is 0 of this generating function. And they occur in mathematics in many ways, and on the other hand, for practical purposes, they're just complicated versions. They're just really just zeta functions. In other words, there's not anything original about them because they're just related simply to zeta functions. Asymptotic series, this is a concept that we need to know about in physics because often in physics, well, in fact, all the time in physics, we can almost never solve a problem exactly, so we use perturbation theory. And we solve an easier problem exactly, and then we introduce the complications slowly, and we generate an expression like this. The mathematicians think of an asymptotic series as 1 over x to the k, ak over x to the k, where x is large. Physicists think of it as lambda is the k, where lambda is small. But of course, you just replace lambda by 1 over x, and it's the same concept. The rigorous definition is that the remainder Rn of x, which is the actual function minus the partial sum, should satisfy this relation, namely that as you, for any given integer like n equals 10, the limit x to infinity of this expression is 0. And the physics expression would be 1 over lambda is the n, the remainder goes to 0. And in this case, one writes that the function you're approximating is this series, and instead of writing an equal sign, you write this, I don't know what the English for that is, but a wavy equal sign. Some authors add the extra condition. I don't necessarily see why. Here's an example of a derivation of an asymptotic series. I invite you to go through it. In physics, what we have is, we write it this way, that Sn of lambda is k goes from 0 to n, some coefficients ak, lambda to k. When lambda is something small, it might be the fine structure constant, which is 1 over 137. That occurs in atomic physics all the time. It occurs in quantum electrodynamics all the time. And so lambda is very small. It's 1 over 137, and a series look like that. Remainders this way, and we want this to be true. And WKB and quantum electrodynamics are examples. I'll just mention this in passing. This is once again an application of the gamma function. Anytime you have, first of all, factorials occur almost everywhere. Anytime you have a factorial, you can replace it by a gamma function, and then you've generalized the hell out of whatever the formula is that involve the gamma function. So, for example, the kth derivative of x to the w is this expression here, or it's w factorial over w minus k factorial times x to the w minus k. Well, you can replace that by a ratio of gamma functions. And now the right-hand side here is defined for w in the complex plane if you avoid the poles. And on the left-hand side, and k can also be a complex number. Now you go over to the left-hand side, and you can have w be complex, which of course is no big deal, but now k can be complex, or it can be a real fraction. So now what you have is a complex derivative or a fractional derivative, and you have the thing well defined on the right-hand side. And once you define it for x to the w, you can define it for any polynomial, for any power series, so you've defined it for essentially all of mathematics. And effectively then, you have the z derivative of x to the w is then this expression here. And so the z derivative of a function f of x is dz dx to the z of this power series expression for f of x, and it's then this expression here. And fractional differential equations then are actually used to describe dispersion, diffusion, fluid flow in complex media. Here is an example of the half derivative, and what I then show is that if you differentiate twice with the half derivative, what you get is the same thing as if you differentiate once with the whole derivative. I think we can skip these electrostatic problems. If some of you are curious, we can do them in the problem session. Let me just skip this. By the way, as I said to you before, biophysics is a good field to get into, and there'll be a course offered in biophysics this spring, the spring of 2020. I think Keith Lidke is teaching it. I'm not sure, it could be Jim Thomas. I used to teach it, but I'm not teaching it this spring as far as I know. I haven't looked at the schedule for the spring, actually. Anyway, it's interesting, and as I said to you, it's just a very interesting field, and the molecular biology is stuff you can learn rather easily, and so then the question is just applying physics to, combining the physics with the molecular biology, and it's interesting, and as I say, you might advance the field of medicine, which would do to lots of people a lot of good. Infinite products are things that I've always found to be quite remarkable. An infinite sum seems to me, or infinite series, which is the subject of Chapter 5, I've always thought of them as kind of prosaic. But infinite product, I think of as slightly magical. In other words, I can imagine what an infinite series is. I can't ever quite imagine what an infinite product is. But of course it's, I mean, I understand it's the limit as you take the right-hand side and you let some capital N go to infinity, but still it's kind of remarkable. Okay, if we have no more questions about Chapter 5, I want to go to Chapter 6, which is more important than Chapter 5, I think, because it's complex variable theory, and there are kind of two aspects to it. One is it's useful, and it's used throughout mathematics and physics. The other is that there are all sorts of very attractive and amusing relations that occur in complex variable theory. And in fact, as I may have mentioned to you, sometimes back in the 1960s and 1970s, thousands of theoretical physicists went down the rabbit hole following complex variable theory and basically wasted their time. That's because it's an intrinsically interesting subject. So but because it's so important, I'm going to do some of this stuff on the board. And so if somebody can turn the camera, I'll go down to this place here. And so the first idea is that we might say that a function is differentiable. And the idea then is that f prime of z is the limit z prime goes to z, and this is the important thing here, of the ratio f of z prime minus f of z divided by z prime minus z. Now, of course, this is what you'd expect, the right-hand side. The part that's important and unusual and specific to complex variable theory is this part, that the limit has to exist no matter how z prime goes to z. So in other words, z might be some point here, and you can have z prime go like that, but z is a point in the complex plane. So for example, there's the y-axis and the x-axis this way, and z is x plus iy. And so z prime can approach this way, it can approach that way, approach this way. No matter how z prime approaches z, this limit must exist and give you the same, and be unique. You must always get the same limit. If you do, then it's differentiable at z. The function is differentiable at z. So that's basically it. That this part of the definition is the remarkable part, and this is the obvious part. So if the function is differentiable at z and differentiable in some small disk around z, or here I said z0, all right, so if it's differentiable at z0 and some small disk around z0, then the function is said to be analytic at z0. So analytic at z means that it's differentiable in a disk around z. Another term that's used is holomorphic. When I was an undergraduate, I took a course in complex variable theory, and the professor was German, and he always said holomorphic. I wish I could reproduce his accent, but I can't. Anyway, let's suppose we think of, so just as an example, because this is important stuff, let's look at a monomial z to the n. So what is f of z prime minus f of z? So this will be z plus dz to the n minus z to the n. And if dz is small, then this is just equal to nz to the n minus 1 times dz. So you see this is going to work and be independent of the ratio, because in this case, this is equal to nz to the n minus 1 dz, and the denominator, this is just dz, and so the critical part, dz, cancels, and so we get nz to the n minus 1, which is just what you would have thought was the derivative of z to the n. So now what you see is that the monomial z to the n is analytic for all z. If something is analytic for all z, we say it is entire. So an entire function is one that's analytic everywhere. Moreover, any polynomial is entire because a polynomial is just a sum, a finite sum of terms like z to the n, positive n. Now, it's worthwhile examining a case that is not analytic, just to show you that not all functions are analytic, and to show you that what goes wrong is this limit thing. Because the ratio here, unless the function is pathological, this is always going to work. In other words, if you let z prime go to z, you're typically, unless the function is pathological, you're going to get a finite number here. But if it's not analytic, you're going to get a different number according to how you let z prime approach z. So as an example, the example here in the book is that f of x and y is x squared plus y squared, and that's the absolute value of z squared. Or in other words, it's z times z complex conjugate. And if we work that out, let's, we're going to compute the derivative at 1, 0. And one way is we can say let x equal 1 plus epsilon and y equals 0. So in other words, here we're computing the derivative of this thing at the point 1, 0. But in the first case, we're approaching this way. We're approaching from the right. And so what's the limit? Well, it is f of 1 plus epsilon 0 minus f of 1, 0 divided by epsilon. So the denominator is quite simple. So we do 1 plus epsilon. Well, it's x squared plus y squared. Y is 0. So this is just 1 plus epsilon squared minus simply 1 over epsilon. And obviously this is 2 epsilon over epsilon, so we get 2. On the other hand, if we approach this way, so we're approaching the same point, but now what we're doing is we're taking f of 1 comma epsilon minus f of 1, 0. And now we have to divide. Now, since y is different, the change in z is iy, because after all, z is x plus iy. Y is epsilon, so dz is I epsilon. And so now we're doing 1 plus epsilon, so this is just 1 plus epsilon squared, subtracting 1, and we have I epsilon. And so now, what is this? This is minus I epsilon, and the limit epsilon goes to 0 is 0. So we take the derivative this way, we get 0. We take the derivative this way, we get 2. So this means that this thing is not analytic. So, any questions about this? Maybe all right. The next thing is the Cauchy-Riemann conditions. And the Cauchy-Riemann conditions follow directly from this definition. It's just that what we're going to do is we're going to write f of x plus f of x and y as a real part, u of x and y, plus iv of x and y. And this is what we're calling f of z. And always z is x plus iy, or almost always. So now, what are we saying? Well, what we're saying is that I'm going to write f prime of z dz. Well, what is that? Well, it's going to be partial u partial x plus I partial v partial x times dx plus partial u partial y plus I partial v partial y times dy. So that's the change in f when we change x and y. And this should be f prime of z times dx plus I dy. And the point here is that, you see, this f prime of z is independent of how dx and dy go to 0. It's the ratio of this divided by that, independent of how x and y go to 0. So for example, suppose we first set dy equal to 0. Then this is saying partial u partial x plus I partial v partial x times dx is equal to f prime of z dx. So equivalently, we can cancel the dx's on both sides, and we get that. On the other hand, the next thing we can do is we can say, well, let's let dx equal to 0. We take the same equation with dx equals 0. What we get is partial u partial y plus I partial v partial y times dy is equal to f prime of z times I dy. So now what we can do is first we cancel the dy's, then we divide through by I, and we have 1 over I. And now we can equate these two things. So what we have is that this thing is equal to that thing. And of course, 1 over I is the same thing as minus I. So these are the Cauchy-Riemann conditions. And one of the things that may surprise you, I think one of the things that surprises students when they first study the theory of functions of a complex variable is that if they have an equation, any equation almost, is really two equations, because a complex equation has a real part and an imaginary part. And so every equation is really two equations. So if we write down the real part of this equation, what is it? It's partial u partial x is partial v partial y. And the imaginary part of this equation is partial v partial x minus partial u partial y. These are the Cauchy-Riemann conditions. So, and I've derived them assuming that f is differentiable at c. So the Cauchy-Riemann conditions then are these. So in other words, if you have a function f of u and v, and you wonder if it's, I'm sorry, not f of u and v. If you have a function u of x and y plus I v of x and y, where this is the real part of the function, this is the imaginary part of the function, and it's a function of x and y, you wonder if it's actually an analytic function of z equal to x plus I y. You ask, does it satisfy the Cauchy-Riemann conditions? And so you just check the Cauchy-Riemann conditions. And for that matter, just as an example, why don't we, since we did this example here, we see there we've got a very funny function. It's a function of x and y, and there's no imaginary part at all. So the function v is identically 0. And so since v is identically 0, u would have to be a constant. Because v is 0, so partial u partial x would have to vanish, and partial u partial y would have to vanish. and yet u, the real part of this, is x squared plus y squared. Well, that certainly isn't a constant. So that's an example of that. Let's suppose instead we take a function that looks like that, but is just z squared. So z squared is it's x plus iy squared. So that's x squared minus y squared plus 2ixy. So here, u is equal to x squared minus y squared. V is equal to 2xy. By the way, I'm just doing this. Well, of course, we've got a video of it, so you can look at it there. Let's see if it satisfies the Cauchy-Riemann condition. And let's use a nicer notation instead of writing this. Let's just use u sub x for partial u partial x. Okay. So in other words, the Cauchy-Riemann conditions then are u sub x equals v sub y, and v sub x is equal to minus u sub y. Okay, so let's look at the top one. U sub x is 2x. V sub y is 2x. Okay. So the first one works. Let's look at the second one. V sub x is 2y. U sub y, well, it's minus 2y, but a minus sign equals 2y. So we see this expression, which we showed earlier, it's just a monomial, so it's an entire function. We see it satisfies the Cauchy-Riemann conditions. Or Cauchy-Riemann conditions. Pronounce the thing more or less much better. Another example, the example I give in the book is 1 over z minus z0. And I would say just look in the book and you can see what the details are there. We've got a few minutes left. Is there a question or shall I plow on? All right, let me plow on to one of the really important results in complex variable theory. And that complex variable theory is such an integrated and logical structure mathematically that it seems to me that what we've gone through so far is maybe 1/4 of the whole subject as far as the intellectual content goes. The thing I'm about to do is another 1/4. And the other 1/2 is just arbitrarily complicated and hard to understand, and we don't need to look at it. Well, not quite, but there's in other words, there are some things that are really important and easy to understand. I think we've done 2 of them so far. Let's do the next one. And the next one is we're going to be doing an integral. And to make it simple, we're going to do something. We're going to go out to L, up to H, back, and then down. And we're going to call this this is going to be a closed contour because you go back to where you started, and it's a rectangular closed contour. We're going to integrate an arbitrary function along the contour. And what is meant by that is, by the way, the LaTeX formula for that is \O_int. So we're going to have u of x and y plus I v of x and y. And we're going to have this dx plus I dy. And we're going to go, at first, we're just going to have dx's, and then we're going to have idys, and then we're going to go dx's but backwards, and then we're going to have idys but backwards, or down. And so this is going to be an integral 0 to L, u of x and y is 0, plus I v of x and y is 0, dx, plus an integral 0 to h, u of L and y, plus I v of L and y. So it's L because x is equal to L on this upper leg. But this is I dy, because dz going up is I dy. And then the rest of it is an integral from L to 0 of u of x, but y is equal to h. H down to 0, u of 0 and y, because x is 0 here, plus iv of 0 and y, and it's I dy. So what I want to do now is look at the real and imaginary parts of this contour integral. And then I want to apply the Cauchy-Riemann conditions to it. Or to them. So let's focus on the real part first. The imaginary part is just basically the same thing. And so, since we're almost out of time, so the real part of this thing then is integral 0 to L u of x in 0 minus u of x in h dx, and then minus integral 0 to h v of L and y minus v of 0 and y. dy. Okay, so in other words, the real part of this is this term where you have two factors of I, this term, and this term where you have two factors of I. So you get that expression there. Now here's the cool thing. You see, this thing is just an integral of the y derivative of u integrated from 0 to h. In other words, u of x comma 0 minus u of x comma h is equal to minus the integral 0 to h u sub y of x and y dy. On the other hand, this thing is an integral of the y derivative of v. So v of Ly minus v 0y integral 0 to L v, actually it's v sub x, I should have said, v sub x of x and y dx. And so this whole thing up there is equal to minus the integral 0 to L, integral 0 to h, of u sub y, the y derivative of u, at x and y, dy dx, minus the integral 0 to h, integral 0 to L, the x derivative of v, x, y, dx, dy. Or if we combine the two, it's minus integral 0 to L, integral 0 to h, uy of x and y, plus vx of x and y, dy dx. But the Cauchy-Riemann conditions tell us that that's 0. That is to say, u sub y is minus v sub x. So consequently, u sub y is equal to minus v sub x. So this is equal to 0. So the real part of this contour integral is equal to 0. In the book, I go through in detail the y part. In fact, I think on Thursday, I'll, on the board, go through the y part again and show you that the y part, the imaginary part of the contour integral is 0. And the generalization of this is the following. If you have any region in the functions, a function f of z is analytic in here, and you do any contour inside the region of analyticity of f of z dz, you always get 0. So this is Cauchy's integral theorem. And it is, it's another, from the point of view of the intellectual content in complex variable theory, this is like 25% of the whole field in my book, as far as the importance of it goes. And you see it's fairly easy to understand. I'm going to go through, because it's so important, I'm going to go through different derivations on Thursday of this. All right, let's quit. And any questions? All right, why don't you push that button and turn it on.